Kia ora, I'm Catherine, and this is my water availability model. Regional councils are required to set limits on water resource use, the biggest use in Canterbury being irrigation. And that's so they can try and ensure sustainable management of water resources. What that effectively means is that there will be water available for our cultural and recreational needs, as well as our economic uses. So what I wanted to do was create a tool that a water planner or a water researcher could use to access flow data, plot it, see what patterns there were, and then run scenarios of how a change in abstraction or water take would alter the river flows. So you make your selections on the left-hand side here, and a plot will appear on the right-hand side. So let's have a go. So I'll start by selecting a river at the top here. There are 18 Canterbury rivers to choose from, ranging from the Wyo in North Canterbury down to the Waitaki in South Canterbury. I'm going to select our nearest biggest river, which is the Waimakariri, and click Fetch Data. The program's now sending a request to the eCan server. They provide river flow data through their API. It takes a little while, around 30 seconds, for the data to be sent back. You can see the data's loaded when the data quality readout appears. This gives information on what time periods are available, how many missing or negative values there are, and what percentage of data falls into the quality bands. These are defined by the National Environmental Monitoring Standards. Now we can select a plot type, so I'll start with hydrograph, and we'll see what gauging stations are available. There are 2 available on the Waimakariri. I'm going to select them both. Now a time period, I'll go for the full 14 years available. And data frequency, we'll stick with raw data and see what happens. And I click plot data. And a plot appears, and we can see with raw data there's not much that can be made out from that, except that there's been a few very high flood events. So let's change raw data to monthly flows instead and plot that. This is much more helpful. And actually what we can see here is that Waimakariri at below Otarama only starts in 2016, and if we look back at the data quality, yes, that's clear, it says that there. So let's look at something else. Well, maybe we don't want the full 14 years, maybe we just want the previous day. So we'll look at that, and we can have hourly flows or raw data, so let's pick hourly flows. Here we can see what's been happening over the last 24 hours. It's been raining, so flows increased, and we can see that flow at Old Highway Bridge does tend to lag Otarama, which you would expect because Otarama is upstream and Highway Bridge is downstream. So let's have a look at a different plot type. We'll try flow duration curve. Again, we'll look at them both and click plot data. Now flow duration curves show the percentage of time that a flow is above a certain value. So here that would be 100, and flow in the river is above 100 about 50% of the time. And we can see that Otarama tends to have a slightly higher flow than Old Highway Bridge. The third plot type is average monthly medians. Here we can only select one location, so we'll try Otarama, and perhaps we'll go for the previous 5 years. It doesn't matter what data we select because the calculation will be done on raw data anyway. And here we can see the monthly medians. So March is a particularly low flow month, and June is a very high flow month. And also plotted is the mean annual low flow. That's the average of the minimum flows for each year, which is just above 40. Now that information is going to help us run a scenario. So whatever we allow take to increase by, we know that we don't want the flow to fall below minimum annual low flow. So that's just above 40, so perhaps we'll set the threshold at 50. And we'll say we're going to increase abstraction from the Waimakariri. Maybe we'll try 10 QMEX, which is a lot. And then we'll run the scenario. And a flow duration curve is produced. And this gives the unaltered flow, the Waimakariri, which is blue. And then the altered flow, what would happen if you did take an extra 10 QMEX out, but then you had to stop when you hit the minimum flow level of 50. Here is an example for the Selwyn River, where there's been lots of press about it running dry in summer in recent years. I've looked at the median monthly flows, and you can see here that the mean annual low flow is well below 1, quite a bit different to the Waimakariri. So in this case, I'm going to run a scenario where instead of increasing abstraction, I'm actually going to put water back in the river. And I wouldn't need a threshold to run that scenario. So let's see what happens. Here we are. So the blue line is the unaltered flow. And we can see that the Selwyn does get down to extremely low flow, almost zero in fact, on some occasions, a very small percentage of the time. But if we were to put 1 cubic back into the Selwyn, or conversely stopped taking out 1 cubic from the Selwyn, which it would be a lot, then we can see that it never quite gets down that far. It's always above 1. Now these are purely mathematical results, of course, because this program doesn't make any attempt to model hydrological processes. Finally, once we're completing our scenario work, we can click Export Data. And this will save a CSV file of the raw data in the same location as the main.py file. So to sum up, I think one of the most challenging things I found was just not having enough time to implement all the ideas that I had, and also trying not to be too repetitive with my code. Sometimes you just want things to work, even if the solution's not very elegant. I've really enjoyed developing this model, because when you do solve an issue and a plot suddenly appears, it's a great feeling. Thank you for watching.